Hello, my name is Todd Evans and I am a Level 2 Product Support Engineer at Cole Morgan, and this video series is an introduction to the AKD Ethernet IP servo drive. Welcome to video 5 of the AKD Ethernet IP video series using the sample project to control the AKD and generate motion from the PLC. In the last video, we established communications demonstrating enabling and disabling of the drive using the sample project and the AKD enable and disable add-on instructions. We're going to repeat that and then elaborate on using the sample project and other add-on instructions and methods demonstrated by the sample project. This will allow the user to experiment and get familiar with triggering the add-on instructions and basic functionality that the AOIs provide. The user will also get exposure to the best practices for implementing add-on instructions in the ladder and proper timing for triggering them. Note, this procedure assumes the motor is unconnected to any mechanics and is free to turn independent of scaling and units. In this demonstration for units, you will notice I have the AKD drive set up for motor only, and the position, velocity, and acceleration units are all set to custom mechanics dependent. I have the scaling set to 65,536 counts equals 1 rev. This is consistent with Ethernet IP scaling, which we will go into more detail later. For now, note that 65,536 counts equals 1 revolution of the motor, and 65,536 counts per second for velocity equals 1 RPS or 60 RPM, and 65,536 counts per second squared for acceleration is 1 revolution per second squared or 60 RPM per second. I do want to emphasize that Ethernet IP scaling and counts, or counts per second squared, that comes over Ethernet IP is not directly related to the workbench units. In this example, we've set it up so that they are equal and the same, but they don't necessarily have to be, although we consider that to be best practice. Okay, so first of all, the drive is inactive. Everything else is ready. Jumping back to the ladder, the AKD enable add-on instruction, I toggle to trigger it. It's done. I check back and the drive is active. If I go to the next rung, it's the AKD disable add-on instruction, so I toggle it. It's done. The drive is inactive again. Re-enable. Okay, the drive is active. I will go into this in more detail later, but it's a good idea for you to start looking at the ladder logic and methods we use to trigger the add-on instructions in the sample project. You'll notice that we use a one-shot to enable, but then we also seal it in based on that it's enabled and it's either not done or not errored. So it will stay executing every scan until it's either done, successful or complete, or there's an error in the execution of the add-on instruction, meaning there was a problem. It's important to note the different seal-in logic that we use depending on what the add-on instruction is. So for example, with the AKD home add-on instruction, we one-shot it, we seal it in, and it executes for as long as the process complete is not true or it's not errored. So in the case that the process complete bit comes on, indicating that the home routine or the home execution is finished, or error means that there's a problem, error occurred during the execution of the AKD home add-on instruction. Again, look at each add-on instruction and see what our best practices and methodologies are for each one, and don't assume that they're all exactly the same. To demonstrate the AKD home add-on instruction, it is important to note that the AKD home simply performs whatever homing type the AKD drive is configured for on the home screen in Workbench. Assuming default settings, the drive will be configured for a home type 0 current position. This is a non-moving home type where the feedback position will be set to 0 on execution of the home routine. To demonstrate this, I'm going to use service motion to jog the motor off so that the feedback position is some non-zero value. Then I'm going to go back to the PLC, toggle the VIT, process complete, back to Workbench. Indicator lamps show that the home was found and done, and that the position feedback has been set to the home.p, which is 0. Note that we didn't really see anything here because that particular home type occurs very fast in the execution time. Also note that the AKD home block add-on instruction, when it executes, it does the same thing as the start button on the home screen in Workbench, which is start the home.move. Okay, so that we can see this a little bit better, I'm going to change the homing type, and I'm going to choose find a home switch. I'm going to make when it's found, the value is 0 in the negative direction. I'm not going to worry about the speed at this point. Got the home switch configured for digital input 3. And so I'm ready to go. So when I toggle this, you should see briefly the in progress bit turn on while it's seeking that digital input. And then the process complete bit came on, and if I go back to Workbench, home is found and done, and the position is 0. One last thing to note is that there's a timeout in milliseconds. If you set that to 0, this add-on instruction will actually error out faster, and that's put in there so that you can detect an error if you want to limit what the actual time is for the home block to be successful, and you can limit that so that it will error out. Note that the error of the timeout on the AKD home block does not stop motion, so that's up to you to write in your code to detect that if you're homing and it errors out to stop, or some other method to disable and so forth to prevent it from continuing to run forever. Another function that the sample project demonstrates is how to jog forward, jog reverse, and stop. So looking at rung 10, you'll see that the method is there is a toggle bit to trigger the start of the jog axis forward. There's an interlock that we need to be home first. That's because we are currently in service position mode and that we're enabled. The jog block will point to the axis, set up the XLD cell. The direction input 1 will select the forward direction, and you'll notice that the second instance of the AKD jog block with a different name for reverse also sets up the same criteria, but the direction bit or direction value is 0 instead of 1, and the triggering methodology is similar. When you toggle one of these bits, it will jog forward or reverse. If you toggle it off, which will create a falling edge, either one of those will trigger the AKD stop smooth block add-on instruction, and that's how it generates or demonstrates how to do a jog forward, reverse, and stop. As I stated before, in this demonstration, the drive is set up for service position mode, and in this mode, in order to successfully execute the AKD jog blocks, you have to be homed. If in service velocity mode, homing isn't required. Hence, how the AKD jog add-on instruction generates a jog is different depending on the drive op mode. There will be a video later on in this series that covers this topic. Since we homed the drive in the previous step, I will proceed to toggle the jog forward contact on. And then I will go back to Workbench. And you'll notice that I'm jogging approximately at the 65,536 counts per second that was defined in the AKD jog block. Now if I toggle it off, it will have fired the AKD stop smooth. Going back to Workbench, you'll notice that now I've essentially stopped. If I want to go reverse, I'll toggle this back, and you'll notice I'm going in the negative direction at the same rate as before. Back off. The constant values in the AKD jog add-on instructions are in Ethernet IP units. We'll go over Ethernet IP units and scaling shortly. Often customers will ask if these values can be varied by the PLC. The answer is yes. If you use, for example, the speed, if you were to declare this entry as a tag instead of a constant value, then you can elsewhere in your code define what the value of that tag is. Keep in mind, in the case of the AKD jog add-on instruction, the add-on instruction must be false, not enabled, and then true again for the changes to take effect. So now that we've jogged, and you'll note that the feedback position is a non-zero value. So before moving on to the AKD move block, which performs an index move, we're going to rehome it so that we start with a feedback position of 0. So let's go back. I'm gonna change the home type to current position so that we just simply reset the position to 0. I'm going to go back to and scroll back up to the home axis. I'm going to toggle the VIT, process complete. Look at the feedback position, it's 0. Now scrolling down, we'll find the AKD move block. You can see that there's an entry for the move type where 0 is an absolute move type and 1 is a relative move type. In this case, we're going to do relative moves for demonstrative purposes. Later, when you are programming your application, if you need absolute moves, you can change the setting accordingly. As with the AKD jog add-on instruction, the values for XL, decel, speed, and position are in Ethernet IP units, which we will go over later. For now, just know that a relative move of 65,536 Ethernet IP counts will result in 1 revolution of the motor shaft. So we're going to toggle the bit. We're going to see the in progress bit briefly on, and the process complete bit indicates that the move is done. If you were looking at your motor shaft, you will see that the motor made 1 revolution. So going back to workbench, you can see that it did go 65,536 counts. And so if I wanted to do multiples of that, I can go back and I can turn the bit on and off, and that will result in another revolution, and it'll be in multiples of 65,536 depending on how many relative indexes that we moved. Also note, scrolling up towards the top, we have some status indications where we take status from the response assembly, such as it drive enabled, is it homed, is there a general fault, are we in position, and are we moving, and we pass that to some tags for use in the ladder logic. And you'll notice that we're enabled, we are homed, and that we're in position. And scrolling down, we demonstrate how to pass the current feedback position into another tag called position, so that you can monitor this within the ladder itself. And you'll notice that it's 65,536 times 2, or you can look back and see that value in Workbench, and you can see that that's also in the ladder as well. A couple of important things to note is the AKD move block, no matter how many instances you have in your program for that axis, writes to motion task 0 like a scratch pad over and over again. So if you trigger 1, it will populate and execute the move with this data, and if you were to have another instance or change the data and re-trigger the same add-on instruction, AKD move add-on instruction, then it will overwrite this and execute the new data. Also note, scrolling back down to the AKD move block, note the process complete PC bit depends on the on target position bit over Ethernet IP, and this bit is codependent on the AKD drive parameter mt.t pos win. If I go to terminal, for example, The default value is half of a motor revolution. If, for example, on the unit screen, I have the workbench unit set for 65,536 counts per 1 rev of the motor, you will see in terminal that 32,768 is half of a motor revolution. Now this could be a lot or not enough of a in position window depending on the application. Make sure that you see the workbench help for details on this parameter. So now we're going to talk about some of the other add-on instructions in the project and also in the library. We've already demonstrated the AKD stop smooth block when we did the jog. You'll note that essentially the function block does the same thing as the drive.stop or drv.stop. There's another one that's called the AKD shutdown or a hard stop. If you go to the enable disable screen in Workbench and you select the disable mode, it's controlled stop then disabled, then when the shutdown is triggered and executed, it will set the hard stop bit in the Ethernet IP control word, and it will start the controlled stop process, essentially the same thing as when you disable the drive with the software disable, and then it executes the controlled stop then disable. There's a shutdown reset that works in tandem. Once you've commanded this one, then if you execute the shutdown reset, then it resets everything that the shutdown executed. There's a drive fault reset, so in the event that the drive is faulted and you clear the conditions that caused the fault, and executing this will reset the drive. It will be necessary after that to re-enable the drive using the AKD enable add-on instruction. There's some sample code here that allows you to trigger or toggle a VIT, and then it will execute a series of counters and add-on instructions in sequence. And what it does is that each time it executes an AKD get parameter for that axis and the parameter number, and then a tag to store the value, it will get the 10 current faults if they're prevalent at the time. So fault 1, fault 2, fault 3, all the way to 10. If it's 0, then there's no fault for that particular fault number. Also, it demonstrates if you were to create your own code and you wanted to trigger and get a different parameter or some other information in the parameter list for an instance number, then you could follow this convention. It's very similar to some of the other add-on instructions where you trigger it, you one-shot it, you seal it in, and then it's either done or it's errored. If you look, the sample project, we've imported all the available current add-on instructions. There's myriad of different ones that we didn't use in the sample project, but they are available. Check the reference guide for the add-on instruction library for more details of some of these add-on instructions.